So in deadlock avoidance, we'll see that the number of resources required by a process are already available. This check should be done in prior, and if this check should be done in prior, then it means that a process must declare the required resources. Right? A process must declare the required resources, and when a process declare the required resources, then the available resources are checked, right? Are checked. If the available resources are enough to satisfy the need of a process, then we are in the safe state, okay, and that process would be allowed to execute if we are in safe state. But if the resources are not available or maybe already occupied by some other process, then we are in unsafe state, and a deadlock can occur a deadlock, right? So a deadlock can occur if we are in unsafe state. So in the safe state and unsafe state, I already told you, if a system is in safe state, then there is no deadlock. If a system is unsafe state, then possibility of deadlock, right? So avoidance is to ensure that the system never enters into the unsafe state. Now here is the if the unsafe state is when we have some processes which are trying to access the resources more than available resources, and safe state is that when this is inverse, right? Means the available resources are enough to satisfy a process. Okay, so avoidance of deadlock, if we have single instance of resource types, it means that one resource R1 has single instance, then research allocation graph, which we have seen before, is enough to find out to avoid the deadlock, right? Is enough to find out the safe condition, safe state, and to avoid the deadlock. But if we have multiple instances of resource types, then we use the Banker's algorithm, right? In Banker's algorithm, we will add one more thing in the claim in the research allocation graph. In research allocation graph, we had resource with rectangle, we have process or thread with circle, right? Process or maybe thread, right, with circle, and we had an age, right? An age of if P1, if this process request a resource, then this is a request age, right? And if a process is assigned with this resource, then this is an assignment age, right? And here we have the instances. Now if we have multiple instances of a process, then we use this Banker's algorithm. If we have multiple instances of a resource, then we use Banker's algorithm. Okay, now for this we will add also another age, that is the claim age. Claim age is that a resource may be required by a process in future. Now for suppose if there are two resources instances, and this is process 1, right? And if there is this claim age is actually represented by a dashed line. This dashed line represents the claim age. Now if the process may need this resource in future, then this will be represented by this dashed line. Now what we have to do, when a resource request age convert, actually what happens in that if a request age is converted to an assignment age when the resource is allocated to a process, and when a resource is released by a process, assignment is converted to a claim age, right? It means that it is not acquired now, right? Resources must be claimed up in prior to avoid the deadlock, right? Resources must be claimed prior to avoid the deadlock. Okay, so here is the resource allocation graph. We can see that this is a thread and this is an assignment age, this is a request age, and these two are claim age. Remember that claim age always go from process or thread to resource. It will never go in this way, right? Because we have only we only predict, or we only declare that we may need this in future. So once this resource is allocated, then this will convert, once this the need of this resource has arrived, then this request age, this claim age is actually converted into the request age. Now the arrow goes like this, right here, and when this resource is allocated to this process, then this request age is actually converted to the assignment age, and once this is completed, then again it is converted to claim age. Okay, so that was a safe state, because nobody is in loop and both requires are true. Okay, they can be scheduled. Okay, but this is an unsafe state when T2 is already having R2 and T1 may need R2 in the future. Then this state is an unsafe state, because this T1 already declared that I will need resource R2 in future. Okay, she will, in that process, that thread may need this resource in future, may need R2 in future. Now here is the possibility, this can make a possibility of deadlock. Now to avoid this, we have Banker's algorithm, right? For this I will insert a new slide, and okay, let me see if I have. Right, here I have a Banker's algorithm. This is an example taken from your book, right? And we'll see that how this Banker's algorithm actually works. Now for example, that we have three processes, maybe process A, now we have three process A, process B, and process C, right? We have three processes, and these three processes actually I think we cannot write on this, so I will copy this to PPT. Okay, that will be fine, that will be easy, right? Much easier. I'll insert this in here. Okay, so we'll see this example here. Now for suppose this is resource A, these are actually resources, all about the resources, right? These are processes. Okay, so we say that these all are resources. Okay, now this is resource type A, this is resource type B, and this is resource type C. Now for example, A have 10 instances total, right? These are total instances. Okay, now if A for example, if A have 10 resources and B have 5 instances of resources, 5 instances of its resource, and C have 7 instances of resource, right? Now this A can be anything memory, this B can be CPU bus, this can be IO, okay, whatever, or maybe some different things, right? So we now P0, P1, P2, P3 and P4, there are 4 processes. Now what we have to do, we have to find out a safe sequence, right? A safe sequence. We have to find out a safe sequence. Using Banker's algorithm. In safe sequence, now these are the maximum need. This is the maximum need of these processes, means 7 instances of A, 5 instances of B, and 3 instances of C. P0 needs that, okay, and P1 and P2, P3 up to P4, these are the instances required by, right? We also say required, right? Resources required. And what are allocated already, for suppose if we are already in running process and at some time we check, right? We check and that what is the condition, what are the resources allocated to P0, P1, P2, P3, P4. Then we see that P0 has 0 resources of 7, 1 resource of B, and 0 resource of C available, right? It means that how many remaining resources are there? 7 minus 0, 7, and 5 minus 1, 4, and 3 minus 0, 0. It means sorry, for 3 minus 0 we need 3, right? 7, 4, 3 is the remaining need of the resources. And here how many resources are required? If 200 if 200 resources are already allocated while required is 322, then how many resources are available? There is a shortcut for that. You take it as a whole number, 322 minus 200, then we'll say that 2 and maybe 1, right? Only 122 resources are required. So you just minus the allocated resources from maximum need. That's fine, right? You can write it as a number. However, these are actually spaced here because they are represented as different resources, so we put the space, but for the calculation you can combine them as a and deal them like a number, whole number, right? So 322, and while the allocated resources are 200, then required resources are 122. Okay, if this is 902, our maximum is the maximum need, and 302 are allocated, then how much is required more resources? It needs 600 more resources to complete the task. Then we see that if we have 222 resources needed, by P3, then 211 are allocated, and then remaining we need only 11 resources for this. And here we have 433 resources available, 433, and we have only allocated 2 resources. It means that 431 resources are remaining to complete the task. So for example, if we have available resources 332, right? So these are resources available at that time when we were checking 332. Okay, 3 instances of A, 3 instances of B, and 2 instances of C. However, the remaining however other resources are actually already allocated to them. Okay, so what we'll see that now we will create a safe sequence in which these processes will execute and never fall into the cycle in the circular rate. Okay, so what we'll do, we'll see that we have this number of available resources. We'll go one by one and we'll see that which process can be fulfilled for its need from this number. So if we see, then this process, if P0 it requires 743, which is not available. We have only 332 resources, and 743 resources are much larger than that. Then we'll go on next and we'll see that 122 resources are actually resources which can be fulfilled from available resources. So what we'll do, we'll allocate 122 resources to that, and we'll wait for the execution. So in this sequence, the first one is P1. Okay, we have allocated all the resources. We have allocated 122 resources to this P1 and wait for its execution. Now what happens? Here's something which may be very tricky or maybe forgotten by students, that they see that okay, 122 minus 132, okay, remaining we have only 210 resources. Now available we have only 10 resources. No, this is not that thing. We have to wait. We'll wait for P1 to complete. Okay, when P1 will complete, then it will release in total 322 resources. Okay, then 322 resources and 122 resources and 110 resources, then it will become 532. 200 resources are already allocated, and the remaining resources and will be released. So it will be 532 total resources released when P1 is complete. Okay, so P1 is completed. Now we have 532 resources. Now we will again see from very beginning, this cannot be done, this cannot be done, this cannot be done, this can be done, but we will go further and we will see that this can also be done, but we will go in a sequence. So we will select this number, right, this P3 for our next execution. Now we will give from 532 we give 11 resources, and we are remaining with 521 resources, right, and 521 resources, and when this will complete, then 521 resources plus 222 resources. So 3 and 4 and 7, 3, 4, 7 resources are actually released. Oh sorry, 3, 4, 7, 7, 4, 3, 7, 4, 3 resources are actually released from P3. Now we'll see that which one can be fulfilled with these number of resources. So we will come to this and we can see that 743, and we have also 743. We allocate all these resources to this P0, right? P0 is allocated with 743 resources. Now this will execute, and when this will release, then we have total number of resources 7, 5 3, because we have left 0. We have left 0 here, right? When we allocated all, then we are left with 0. But when this P0 is completed, then it will return us all the occupied resources, and 7 5 3 are the remaining resources in our available pool of the resources. Okay, so now we will again check here. The remaining need is 600 and we have 753 resources. Now 753 minus 600, then we have 153 resources remaining if we allocate this. So 600 resources are allocated to P2, and when this P2 will be completed, then 153 plus 902, this is total 5 and right, our resources are released from here, right? Resources released from here are 1055, right? Now when now we have only last process remaining here. This is done, P0 is done, and P2 is done, and P3 is done, right? Now we have remaining P4 here. Now P4 is remaining. How many resources we have at this time? We have 1055 resources, right? And now we see here that 1055, right? 1055 resources are there, right? So in this, what we'll do, that from 1055 we'll deduct only sorry, not only 2, but how much is the remaining need? Remaining need is 431. If we will allocate 431, then 4 and 2 and 6, right? Okay, so we are remaining with these resources. Once this process will complete, the fourth process will complete, we are left with 1057 resources. It means that 1057 resources are released from here, which means that now we have the same number. To verify that you are right in your flow, or in your safe state, or in your sequence, if you are correct, to see this, to verify this, we see that at the end available resources are equal to the available instances. If we are less or more than that, then we assume that there is some mistake in our flow, there is some mistake in our sequence. So make sure that whenever you are attempting such questions, you pay attention to this last process. Last process may come here, may come here, may come here, but this time it comes at the end. This is not always thing, right? It can be anywhere, right, according to the required need, right, remaining need. So I hope you got the Banker's algorithm, and here it's also Banker's algorithm is defined. The same problem is which I have already shown you in previous slide is given here, right? So then deadlock detection and recovery. So this is it. And deadlock detection and recovery, I have already told you that deadlock detection and recovery is a method in which there are two ways to recover from a deadlock if deadlock is occurred. And deadlock detection can be done by resource allocation graph, while deadlock recovery scheme is actually, there are two type of schemes. Number one scheme is to abort all the existing running processes, or to abort the processes one by one to break the cycle. The main theme and the main aim of this approach, this method of deadlock handling, is to eliminate the circular wait. Okay, so hopefully this is it, and so we are done with chapter 8 in deadlocks, and I hope to see you in the online class in the live session for further discussion. Thank you so much.